Hi everyone, in our last video we looked into the concept of electron domains and saw how they impact bond angles in certain molecules. Well, in this video we're going to look into the concept of non-bonding pairs and compare them to bonding pairs and see how this impacts the overall molecular geometry of certain molecules as well as their bond angles. So let's get right into it. Now, for non-bonding pairs, which are essentially just lone pairs, these guys, in comparison to bonding pairs, they have slightly more repulsion. And this reason is because bonding pairs are essentially shared between two atoms. Now, if we were to actually create a sort of power diagram that classifies the bond forces between different pairs, we would classify it as non-bonding pairs holding the greatest repulsive force, and then multiple bonds, and then single bonds. Now, in comparison to those that are in bonds, these non-bonding pairs or lone pair electrons would hold much more repulsion, and that is because of the fact that bonding pairs are generally shared between two atoms. Now, the reason why this hierarchy forms between multiple bonds and single bonds is because of the fact that multiple bonds generally have a higher concentration of charge. And that's because of the fact that they contain 2 or 3 pairs of electrons. And therefore, this is going to take up much more space, and it's going to squeeze the other angles as it has increased repulsion. Now, multiple bonds, just to kind of recap, because they have a higher concentration of charge, i.e. they have much more pairs of electrons than a single bond, it's going to have an increased repulsion. And the effect of this increased repulsion, when we see it in a molecule, is that it's going to take up more space and generally squeeze the other angles. Now, to see how that actually looks like for certain molecules, let's explore the comparison between BH3 and HCOH. Now, BH3, it's going to have the molecular geometry of something like this. Because we have BH bonds and we have 3 of those bonds, we're going to divide 360 by 3, and therefore we're going to get 120 degrees for each of these bond angles. However, for HCOH, which is also a triangular planar but has a slightly different molecular geometry, we are going to get slightly different bond angles. The bond angle between the H and the C and the H is going to be slightly less than 120, whilst the bond angle between the H and the C and the O, this bond angle is going to be slightly more than 120. And the reason for that is because, as I mentioned, we have multiple bonds. We have a double bond right here between the C and the O, and this is going to have a higher concentration of charge, i.e. it's going to have increased repulsion, and therefore it's going to take up more space, and it's going to squeeze the other angles, which is in this case the angle between the H and the C and the H, and therefore it's going to create smaller angles here whilst larger angles here. Now, also something else to note is that because of the increased repulsion between the C and the O due to the double bond, this bond between the C and the O is going to be slightly shorter. And that is because covalent bonding itself is defined as, well, electrons being shared between atoms, and it's technically defined as the attraction between the electrons and also the positive nuclei. And because of that, this distance is going to be much shorter because of the fact that the attraction is much higher due to there being more electron pairs here.